Solar PV Power Plant Controller. In this presentation, we will focus on the Solar PV Power Plant Controller, also known as PPC, and sometimes being called as the Grid Controller. We will also cover the electrical aspects of the power triangle, the power factor, and how it's related to the PPC and the overall grid controller operation. Then we'll move forward with each of the individual control requirements. We'll also tackle PPC hardware selection criteria and recognize those challenges being faced by PV power plant owners or grid operators while working with PPCs, and some common acronyms and terminologies at the very end. From our previous discussion on the areas of the solar PV power plant, within this specific example, the grid controller is centrally located on the substation control building. Power Plant Controller, or PPC, is an intelligent vendor-independent system for dynamic PV power plant control and grid code compliance. To satisfy predetermined set points and modify grid characteristics at the point of interconnection, or POI, a PPC is utilized to govern and control the network inverters, devices, and equipment at a solar power plant. Site operators can send these set points and parameters directly to the PPC or more frequently via SCADA system. A PPC is essentially a system for managing plant behavior in terms of output, revenue, and compliance, as well as grid stability. Although each system has different requirements, most PPCs should be able to control the following parameters: active power, reactive power, power factor, ramp rate, as well as those grid support control requirements like voltage, grid frequency support, and fault ride-through. In addition to regulatory components, PPC devices provides the additional benefit of remote controlling and troubleshooting activities that require the power plant to be taken offline. In order to assist field technicians, remote operation control operators can use the PPC to remotely stop or start those inverters, trackers, breakers, and other components. The PV power plant controller is to be implemented at the plant level logic and utilizes closed-loop control schemes. Real-time commands will then be sent to each inverter via industrial protocols such as Modbus RTU or TCP, DNP3, IEC 61850, or IEC 6870, and the like. The need for a power plant controller for a solar power plant can be summarized into four factors. First off is grid stability. One of the primary roles of a grid controller is to ensure the stability of the electric grid, or in other words, secure the power plant's connection to the grid. Solar power plants generate electricity intermittently, which can cause instability to the grid if not managed properly. The grid controller ensures that the plant's output remains within the limits set by the grid operator, preventing voltage and frequency fluctuations that could lead to power outages or damages to electrical equipment. Second is efficiency. The grid controller optimizes the operation of the PV plant by controlling the output power to meet the demands of the grid. It ensures that the plant generates the maximum amount of power while maintaining its efficiency, reducing the plant's operating costs. Features like intelligent control in near to real-time functions maximizes the power plant's availability, thus leading to a more efficient operation. When it comes to safety, the grid controller monitors the power output of the PV plant and automatically disconnects it from the grid in case of abnormal conditions, such as overvoltage or undervoltages. These are sometimes called as intelligent or immediate fault detection. This protects the plant and the grid from damages, ensuring the safety of personnel and equipment within. The PPC's capability to detect and resolve equipment faults or failures helps to maximize the system's power output by utilizing the availability and performance of all resources. And lastly, is all about revenue compliance. Grid operators require a grid controller to ensure that the PV power plant complies with the regulations and standards set by the authorities. This includes ensuring that the plant operates within the voltage and frequency limits and meets the grid code requirements of each country's specific grid regulations to avoid certain penalties. With more solar power plants being integrated into national grids, it has become more difficult for national grid regulators to have a smooth commissioning while maintaining the grid stability. As a result, the regulators are forced to define fixed criteria and set of requirements. This is what's being called the grid code, and compliance is mandatory for solar power plant operators before they can inject power into the national grid. Even if these rules vary a lot between countries, essential functions need to be handled whenever a solar PV power plant is integrated into the grid, such as active and reactive power, as well as voltage and frequency regulations. For grid-tied power plants, it has now become a necessity to use solution based on power plant controllers because of the ease they offer in running the power plant. Utility PV power plants have power purchase agreements or PPAs, as well as interconnection agreements or IAs. These explicitly require the ability to curtail or adopt a certain power factor. Lower megawatt sites that aren't subject to these agreements generally turn on the inverters and plant equipment and let them self-regulate their outputs. When it comes to system size, the chance of putting up a PPC demand rises with the plant size. The larger the PV plant, the larger the likelihood of a PPC requirement. While there's no standardized capacity threshold, most sites above 10 megawatts require a power plant controller. However, some sites that are slightly above 5 megawatts have PPC requirements. Once a site hits 15 or 20 megawatts, the requirement for a PPC becomes pretty common. In this part of the presentation, we'll focus on understanding the relationship between power triangle and power factor in AC circuits. Understanding these concepts are crucial for anyone working with AC circuits, as it can help improve efficiency, reduce energy costs, and ensure safe and reliable operations of our PV power plants. Before we move further, let's make sure we are all aligned on where on the power plant our discussion is going to focus on. Please note that the electric current flowing from the solar modules or arrays going to the inverse is a purely resistive DC, wherein power factor is not occurring as there is no concept of the phase angle between voltage and current. From the inverse to the medium voltage transformer, DC has been converted to AC, wherein it can be classified into three parts: active or real power, reactive power, and apparent power. When we talk about the PPC or power plant controller, the discussion focuses on the AC side, from the inverters to the transformers and eventually to the grid. This means that the lowest level of control functionality is at the inverter level. Since we're talking about a solar PV power plant, which is a power generator, not a consumer, from this point forward, all discussions about the power triangle concept is focused on power generation. The power triangle is a graphical representation of the relationship between the apparent, real, and reactive power in an AC circuit. It helps us understand the concept of power factor. In this example, we will use a leading power factor. Real power or active power is represented by the horizontal side of the power triangle. It's the actual power that is produced and used to perform work in an electrical circuit. It's being measured in kilowatts or kW. Reactive power, represented by the vertical line of the power triangle, is the power that oscillates between the source and load due to the inductive or capacitive elements in the circuit. It's being measured in kilovolt amps reactive or kVAR. Apparent power, represented by the hypotenuse of the power triangle, is the vector sum of real power and reactive power. It represents the total power generated by the circuit, and it's being measured in kilovolt amperes or kVA. The best way to represent it, which a lot of people can relate to, is by using the famous beer analogy. Here we have a glass of our favorite beer. The drinkable or liquid beer represents our real power in kilowatts. This is used to perform useful work in an electrical circuit. More often than not, we have beer foam. This represents our reactive power that is being measured in kVAR, in which there will always be due to the inductive or capacitive elements in the circuit. The combination of these kilowatts and kilovolts amp reactive, which are drinkable beer and foam, is our apparent power being measured in kilovolt amps is being represented by the whole glass. In this scenario, where there's a lot of foam and there's not a lot of beer, so we're not getting the most value out of our purchased glass. This is not ideal as we paid for the whole glass and the amount of drinkable beer that we're getting is not nearly what we paid for. Similarly, with the current setting and comparing it with our power triangle on the right, we can see that the apparent power is at an angle between the real power. Reactive power in most cases does not generate revenue as utilities pay for only real power and not reactive power. Keeping it simple, within the whole glass, the more liquid beer we have, the less foam there will be, which is getting more value for the same costs just by realizing the ratio of the liquid beer to the whole glass. The same concept applies to AC circuits. Power factor is therefore the ratio of useful or real power in kilowatts divided by the apparent power, which is what we're charging for in kVA. So it's telling us how much value for money we're getting for the power we generate for the solar PV power plant. Generally, power factor is expressed as a percentage, for example, 95%, but can also be expressed as a decimal value, for example, 0.95. If we are to stick with the decimal value, we can say that the power factor is a number between 0 and 1, which indicates the design and management quality of an electrical installation. The ideal power factor is 1, which is also known as the unity power factor. A poor power factor with a value towards 0 will produce a more reactive power, which we consider as wasted power, reducing the efficiency of the circuit, while a system with a power factor closer to 1 or unity will be more efficient. This is because a circuit with a low power factor requires more current than the same circuit with the power factor closing to 1 or unity. A power factor of 1 or 100% means all the power is effectively converted into work. In real-world application, the power factor typically ranges from zero point 0.8 to 0.95. Power factor correction is essential when a PV power plant is connected to the grid for several reasons. Power factor correction helps to minimize power losses that occur when transmitting power over long distances. These losses are caused by the reactive power component of the AC circuit, which is not used to perform useful work, but instead circulates back and forth between the source and the load. Power factor correction reduces the reactive power component of the power, which in turn reduces power losses and improves the efficiency of the transmission. In terms of regulatory compliance, many utility companies have regulations in place that requires PV power plants to maintain a specific power factor when connected to the grid. Failing to comply with these regulations can result in penalties and fines. Power factor correction helps to stabilize the grid by reducing voltage drops and other power quality issues that can occur when reactive power is not managed properly. This is especially important in larger PV power plants that can have a significant impact on the overall stability of the grid. Power factor correction allows PV power plants to operate at a higher capacity, which means they can generate more power and sell it to the grid. This not only improves the profitability of the power plant, but also helps to meet the increasing demand for renewable energy resources. In conclusion, understanding the power triangle and power factor in AC circuits is essential for optimizing energy usage, reducing losses, and improving the overall efficiency of our electrical systems. Implementing power factor correction techniques can lead to significant benefits in terms of cost saving, reliable operation, and sustainable energy consumption. Optimally, a solar PV plant appears to the grid as a single unified source of power. When we talk about power quality, it is often useful to think about it as a compatibility problem. Ideally, from the solar PV power plant, voltage is supplied as a sinusoidal wave having amplitude and frequency defined by national standards with zero impedance at all frequencies. However, real-life power grids can present different deviations from these ideal conditions, creating compatibility problems and even grid instability. Factors such as overvoltages and undervoltages caused by grid impedances and load consumptions, over and under frequencies caused by heavy loads or connections or disconnections, excessive real power consumptions. The goal is to maximize power output and therefore revenue, while supporting a stable and reliable grid. Solar PV power plants can accomplish this by regulating active and reactive power through the PPC. The typical control requirements for a PPC are anything involving production in terms of kilowatts and kilowars. Those are active and reactive power. These are active power, reactive power control, power factor, ramp rate, and those grid support requirements like voltage control, grid frequency support control, fault ride-through capability. The PPC must be able to support the power plant's startup and shutdown. Let's look closely at a solar PV power plant, which a PPC is installed. Here is your typical power plant, where you have your solar arrays, inverters, medium voltage transformers, switchgear, and your substation. For data collection, we have your SCADA system and a site-level revenue grade meter that is connected to the POI or point of interconnect. Since we're following regulatory compliance, we will add in a PPC or a power plant controller, which reads data points or parameters at the inverter level as well as the site level POI meter. During production hours, we should expect the PV system to generate power and send it to the grid. These are represented by these red lines. When there's a need to control grid management services, signals usually come from the grid operator, which sends the signal to the control room operator or your ROC. The ROC operator then sends the signal or set points to your PPC through the SCADA system. At the power plant controller, the set points from grid management services are received and compared with the values measured at the point of interconnection. Based on this comparison, the power plant controller calculates the required control values and transmit these values to the inverters. Digging deeper into the PPC operation, the plant controller reads the following data from the point of interconnection: active power, reactive power, voltage, and power factor. The values that the power plant controller receives are being measured at the point of interconnection, processed by a power analyzer, and transmitted to the power plant controller as analog values or via Modbus protocol. Grid management services signals usually come from the grid operator, which sends those up-to-date references to the control room operator. The power plant controller can receive set points in digital and analog form and via Modbus protocol. In some use cases with externally accessible PPCs, references can also be received from the grid operator by an optionally integrated protocol converter conforming to IEC standards. The active power reference is tied to the ramp rate control function to generate a new active power set point. The combination of the reactive power reference, voltage, and power factor reference serves as components for the new reactive power set points. Transmission of the updated control references or set points from the PPC to those central inverters, cluster controllers, or inverter managers devices takes place via Modbus TCP. If you're enjoying this video so far, make sure to hit that like button and share it as applicable. As always, your feedback is most welcome, so please don't hesitate to add your input in the comment section below. When we talk about on-demand active power control, it's usually performed in the range of plant nominal power or within contractual limits. The output active power of the solar PV power plant is constrained to a predetermined power or megawatt limit at the point of interconnect using an absolute production constraint. The PPC's role is to keep the active power output at a fixed commanded set point or react to curtailment commands by operators and the load dispatching center. Typically, this is undertaken to prevent overloading of the distribution system. As long as this curtailment command is active, the PPC must ensure that the output of the power plant does not exceed the specified limit. For example, you have a solar PV power plant rated at 100 megawatts, but needs to be temporarily scaled down production to a new set point of 30 megawatts. The plant must be able to respond to the curtailment request from the ISO and adhere to ramping requirements. The new set point is entered via the SCADA system, prompting the PPC to interact with the field inverters to ramp down production and hit that new set point. The solar PV power plant must begin the alteration of the absolute production constraint set point within 2 seconds and must complete it within 30 seconds of receiving the modification order. This is especially important for plants in the US, like those in California, that are participating in the real-time energy market. With our previous example about the 100 megawatts PV power plant to temporarily scale down production to 30 megawatts, this process is widely known as curtailment, meaning the solar PV power plant's output is being reduced from what it can actually generate at a certain point in time. We can summarize that the curtailment control mode is used to limit the output of the solar PV power plant. In this control mode, the PPC limits the output of the solar PV power plant to prevent the grid from becoming overloaded. This control mode is typically used during productions of high solar PV power plant output. When it comes to solar PV, the action of limiting the inverter's power output is by modifying the DC bus voltage to move away from the system's maximum power generation. I can work on a more comprehensive presentation about curtailment and share it with you guys once available. When we talk about reactive power controls, we need to understand how reactive power flows in the PV power plant and its effect on grid parameters. Using the measurement at the point of interconnection or site level meter, we can see the reactive power generation of our inverters. If the inverters are generating reactive power or VARs and pushing it to the grid, here's what's happening. It rises the grid voltage and moves the power factor to a leading direction, meaning positive. On the HMI or within the PPC interface, a positive sign next to the reactive power set points denotes that the plant should export or generate reactive power from the grid at the point of connection. The exact opposite is happening. If the inverters are absorbing reactive power or VARs from the grid, or a negative reactive power is being measured at the point of interconnection, it decreases the POI voltage and moves the power factor to the lagging direction, which is negative. On the HMI or within the PPC interface, a negative sign next to the reactive power set point denotes that the plant should import, absorb, or consume reactive power from the grid at the point of interconnection. In most cases, reactive power does not generate revenue, as utilities pay only for real power and not reactive power. The reactive power control mode is used to regulate the reactive power of the solar PV power plant. In this mode, the PPC adjusts the reactive power of the solar PV power plant by changing the voltage at the POI. This mode is typically used to improve the power factor of the solar PV power plant. Power factor control is an additional requirement in controlling reactive power, making sure that the plant can stick within the limits or maintain a desirable power factor at the point of interconnection. A couple of illustrations shows a solar PV power plant's power factor measurement at the point of interconnection on a given day, and it's being represented by the red line trend. On the left, we can see that the power factor measurement at the point of interconnect has been jumping up and down from 95.5 to 100. This is the result of a PV power plant operating without power factor control. On the right, a measurement of 0.99 can be seen throughout the day when power factor control is enabled. Grid-tied PV inverters are voltage-controlled current source asynchronous generators. All the utility and respective independent system operators are the ones defining the technical requirements for PV power plants to stay within a certain voltage range to support grid stability. This requirement can be fulfilled with the use of a PPC to regulate reactive power through automatic voltage regulation control. AVR is an explicit interconnection requirement. In this example on the right, which is for a solar PV power plant in California, the system has the capability of producing a net power factor of 0.95 lagging at the point of interconnect when voltage levels are below zero point 0.9 and 1.0 per unit, and absorbing a net power factor of 0.95 leading at the POI when levels are between 1.0 and 1.1 per unit while the generating facility is at maximum real power output. When we talk about grid frequency support, it's directly related to the real power output of a solar farm. Frequency control adjusts the active power in response to high or low frequency events. Active power control may be used to automatically support the grid in over-frequency or under-frequency incidents, based on grid operator power frequency curve and related grid code requirements. The grid code curve are configured during PPC design and commissioning, and basic parameters may be changed also using the PPC user interface to properly define both over and under frequency parameters. As shown on the figure in the right, when the grid frequency changes, for example from 60 Hz to 61 Hz, the active power injected by the inverter is reduced accordingly to a user configurable droop curve. The fault write-through capability of the PPC allow PV system to continue operating even if the grid experiences certain disturbances like specific low, high, and zero voltages or low and high frequency ranges. In addition of a power quality analyzer is necessary to capture short-term grid events, as situations like these only lasts about 1 to 2 seconds, and the PPC should have the capability to adapt accordingly. Temporary faults are frequent and create inescapable variations in voltage, current, and frequency. This functionality is also critical during natural disasters. Another standard PPC functionality is its ability to provide the needed control of the PV power plant during startup or shutdown. The active power management function reduces plant output while maintaining the required ramp rate. This functionality is also essential during varying low irradiance conditions throughout the day where the PPC needs to gradually increase the plant's output by adjusting the inverter's output and turning on individual or block of inverters in sequence. Selecting the appropriate hardware for the PPC of a solar PV power plant is critical to ensure the smooth operation and optimal performance of the PV power plant. The hardware selection criteria should take into account the following. Scalability. The hardware selected for the PPC should be scalable to accommodate any future expansion of the solar PV power plant. The plant may need to be expanded in the future to meet increasing energy demands. Therefore, the PPC hardware should be able to handle the additional capability of the solar PV power plant either with vertical or horizontal scaling. Reliability. The hardware selected for the PPC should be reliable and have a long lifespan. The PPC is responsible for smooth operation of the solar PV power plant, and any hardware failure can result in a loss of revenue and productivity. Therefore, it is important to choose a hardware system that has a high level of reliability and can withstand harsh environmental conditions. When it comes to compatibility, the hardware selected for the PPC should be compatible with the other systems in the solar PV power plant. The PPC needs to communicate with the inverters and other components of the PV plant. Therefore, it is essential to select hardware that can integrate well with the existing system and communicate effectively. When it comes to security, the hardware selected for the PPC should have a high level of security to prevent unauthorized access. The PPC controls the flow of electricity in the solar power plant and any unauthorized access can result in a security breach. Therefore, it is crucial to select a hardware system that has a high level of security features to prevent any unauthorized access. When it comes to cost, the hardware selected for the PPC should be cost effective and within the budget of the solar power plant. The plant should aim to maximize its return on investment while keeping the costs under control. Therefore, it is essential to select a hardware system that offers the best value for money while fulfilling all the other requirements. The hardware selected for the PPC should be easy to maintain and repair. The plant may need to carry out routine maintenance and repairs on the PPC hardware. Therefore, it is important to choose a hardware system that is easy to maintain and repair, and spare parts are readily available. When it comes to performance, the hardware selected for the PPC should have a high level of performance. Again, the PPC is responsible for managing and optimizing the generation of electricity. Therefore, it is essential to select a hardware system that can handle the load and deliver high performance. By taking into account these considerations when choosing the right hardware system, the solar PV power plant can maximize its return on investment and meet the increasing energy demands of today's world. As of 2020, there are two main hardware choices for PPCs, and this has been a battle between traditional PLCs and industrial PC-based control systems. Both of these have their own pros and cons, and the choice of the right hardware might vary with the PV system owner's preference as well as compliance with national and international grid codes. This is what we're going to cover next. A programmable logic controller, or PLC, is a hardware that controls devices or processes based on pre-programmed, closed-loop, or ladder logic. PLC has its own advantages. First off is ruggedness. PLCs are made for reliable operations in very harsh environments. It also offers the ease of programming and troubleshooting, as it usually follows scan-based programmable software. Proprietary processors and unique operating systems, PPC has the resistance to viruses and cyber attacks compared to an industrial PC. A conventional PLC can keep operating even if a server goes down due to its pre-programmed automatic function. PLCs have long life cycles and can last up to 15 to 20 years of operation, and it is used in nearly every industry, not just for PPCs. On the other hand, PLC also has some disadvantages. The primary thing that sets PLC control apart from PC-based controls is built-in or snap-on input-outputs or IOs. Many types of IOs can be combined in a PLC. However, IO options are limited since they're tied to the same manufacturer. PLCs can also be expensive. Always comes at a higher cost than PC-based controllers. So scaling a PLC in the same way as an industrial PC is not always possible and could lead to additional cost and complexity. On the other hand, a PC-based PPC is a software that is installed on a server on an industrial PC that can run on Windows, Linux, or other operating systems. Industrial PCs have a long list of advantages. The fact that PCs are designed to be more application agnostic and less hardware oriented allows for evolution to take place more quickly. PCs tend to be a much more open architecture, which would allow for a variety of different software and hardware to be used depending on the application requirements. Industrial PCs can be used for multiple tasks beyond the cyclic control task, like historical data storage and extraction. Maintenance and replacement may be significantly easier and options to upgrade abound are always open. More often than not, industrial PCs from one manufacturer can be replaced with an industrial PC from another. When processing or computing power becomes a limitation, there are always usually that option to upgrade the processor speed, memory, part options, or number of network interface cards. Industrial PCs also have easy connections to the network using Ethernet connectivity. This allows for a more streamlined, purpose-built control architecture that is flexible and scalable. New industrial PCs are even more resistant to harsh environments and extreme temperatures. Although there are also some disadvantages using industrial PCs, like if a server or PC is compromised and goes down, PC-based controller will no longer be intact, functional, or operational. This can cause non-compliance issues with the PPA or IA. For Windows-based industrial PCs, and there's a need to upgrade the operating system, this can be difficult. If we are to put those two hardware side by side and focus on their advantages, we can see that cost and scalability are very much in favor of a PC-based solution. PCs will be easier to scale than a PLC-based application, as they can easily updated to handle more data processing by simply adding more memory or processing power. In addition, you need to ask these questions while your plant is operating. Do I need to store a large amount of data locally? This is a clear benefit of an industrial PC, where storage space is easily scalable. Do I need an integrated HMI? This is also a benefit for an industrial computer, where the machine builder can minimize the number of devices by adding the HMI application or installing it on the industrial PC. In conclusion, PC-based controllers offer a lot of value and should be considered. A full-fledged PC can bring many advantages due to its sheer computing power. Industrial Internet of Things, IoT integration, databasing, and high-level languages are all very desirable in automation applications, and these are very achievable with PC-based controllers. The most robust solution consists of two embedded PCs with solid-state drives running industrial-grade software packages. The first PC is configured as the primary data concentrator, while the second PC runs the SC or grid controller programs, as well as engineering and analytics program, and would also serve as the backup for the first PC. At this point, we'll cover some operational challenges involving the PPC. Loss of synchronism. Large PV systems are comprised of many inverters distributed across a wide area. With that in mind, voltage profiles along radial lines within the plant must be managed properly. The PPC must be able to control all inverters in a coordinated fashion to achieve a target POI value. Communication delays. In the plant level control, the POI frequency and voltage are measured for the frequency power droop control and voltage control. The plant level control generates real power order and reactive power order for the inverter level grid following control. Communication delay of 100 millisecond to 300 millisecond is expected. Delayed reactive power support from the plant level control may cause inverter voltages after fault clearance. When it comes to oscillations, if the grid is relatively weak, the inverter real power control and the plant level voltage control are not that fast, oscillations will appear in real power, reactive, and voltages. It is often found that parallel inverters may oscillate against each other. The circulation may manifest as real power oscillation, reactive power oscillation, or both. They oscillate against each other in real power if the real current related droop controls are assuming different values, and they oscillate against each other in reactive power if the reactive current related droop controls are assuming different values. This will give out false readings to the PPC. At this point, I'll leave you guys with those acronyms and terminologies that was used during the presentation. As always, if you enjoyed this video, please don't forget to hit that like button, provide some comments, and consider subscribing. Thank you all guys for watching.